postdoc to use PowerPoint, but some of them still use Beamer.
Yeah, I mean, I used Beamer. I joined Maryland, and then I realized that it was crazy, right?
Yeah,
Beamer is great. It really takes too much time.
I mean, later on when you need to sell your stuff more, you need something to be more vivid.
Yeah, well, that's fair.
Yeah. We are really into job talk, so you suddenly realize you are not. Unless that is a pure theoretical discipline.
Yeah, no, I mean, if you've just a lot of formulas, it's always okay, but just to start putting things together, plots, and it becomes very complicated.
Maybe the right, it's beautiful here. It's,
yeah,
follow leaves.
I mean, the institute is beautiful, actually. Yeah,
yeah. If you're on the airplane, you can see it.
So now I learned how to work out that kind of last time. So now in Zoom, like everybody sees before. So in Zoom, I'm not making that kind of so people on Zoom will see the people
Good.
Who asks questions and how many people.
Well, it'd be nice to have a camera from there.
Do what?
A camera from there, so they really see what.
From
there, I have to guess who is from behind.
We have it in Maryland, but it doesn't work.
Huh?
We have it in Maryland, but it doesn't work, so it's impossible to change from one camera to the other. I don't know if you had the same problem when you were there or when with an update.
But when I was in Arizona, they had this super fancy camera. It's like 36 degrees camera, and it focuses on the people who are speaking.
We have this it's called the like
I see.
This animal. It's bird.
So we have that here.
We have one or two here. The experimentalists do them. They keep them. There's always in some way.
Right.
Yeah, that one. So when I was there, it's functioning because I helped set things up.
You okay? I see. We didn't manage anymore, so
yeah. Some postdocs who are interested in fixing stuff. Let's somehow there's a fluctuation today. I don't know what happened to the students. Let's not wait any further. Okay, today we're really happy to have Lorenzo Ricci from Maryland to give us a talk. Lorenzo graduated from EPFL, working with Rattazzi and User, and now he's in Maryland as a postdoc. Working with many different group members there. He worked a lot on BSM physics from different aspects. Today, he will give us a talk about exploring the flavor of the TeV. Please go ahead.
okay, thanks. Thanks a lot for the introduction. Thanks a lot for having me here. So I decided to present some of the results of a work that we've done in collaboration with QWO, Riccardo Rattazzi, and Luca Vecchi, and we posted earlier this year. Now, I don't want to spend really much time on the introduction to say obvious things. Just let me say the basic, so that we are all on the same page. In this talk, I will always talk about the physics, so some BSM, which is heavier than what we can test, and that we can canonically describe in terms of an effective Lagrangian. And this effective Lagrangian, as we know, describes all these new physical effects with many new interactions that we can measure. And what we know about this interaction, we know that this interaction, they spread along different order of magnitudes. So the typical size of this interaction is very different. It is actually even probably outdated. It's 20 from the European strategy and goes from few TV for precision test and the researches at the LHC up to several TV in the case of flavor. So in this context, a natural question to ask is where is lambda and which kind of physics can we find at the different lambdas? Where lambda, again, is the state of possible in physics.
Just to make sure in this
Yeah.
plot, I assume there's a single operator affecting those observables,
Yeah.
and I'm labeling by the
Yeah.
operator. So what are the difference between the solid?
These are projections for Illumi.
And the hash.
And of the Illumi. Dash, I guess they are marginalizing over the different operator. So it's either single operator rich or you're doing some marginalization. But this is just an invitation, so okay.
There are so many different flavor observables, right?
Yes.
So this one is select this field that people are.
Yeah, this is my next slide. So just focusing on what we will care for the rest of the talk. Basically, the scales that we care are the electroweak scale, the scale that we can test directly at the LHC, and the scale that we will eventually test at the CCHH. We picked this collider just as a benchmark of the largest direct reach we can, at least right now, imagine to have on Earth. And among the other interaction, the flavor interaction that we care about are all these order of magnitude, so 10 to 7, 8, maybe even 9. GV, this bound actually, I mean, would be more precise later on, but comes from epsilon k, imaginary part. And again, in this context, where is lambda? And we have to basically consider all options to ask this question. One is that lambda is very far away in the UV, even up to the Planck mass. In this case, there is not much that I can say that probably none of us can say, because this new physics is too heavy to be interesting for us. First of all, because we cannot access the new physics, and secondly, because if you can, it's hard to imagine physics can explain the trick sector. But that's a secondary aspect. The first one is that this physics is not accessible.
Yeah, but this.
Yeah.
But this is a bit too quick, right? Because lambda here, you're calling it 10 to the 7, 10 to the 8. Doesn't necessarily mean that the new states could appear much lower, right?
You can.
Yeah, there's a weak coupling there.
I mean, this is the generic scale where, I mean, it
No, I'm just saying that you're putting all the couplings into one parameter, but
Yeah.
there's couplings in the numerator as well as the denominator.
Absolutely.
Yeah, so this could be, the new physics could be lower than that.
Absolutely. That's the next slide. Okay, that's actually the word talking against PCP would be basically to characterize in a UV complete setup all these effects to really have a precise determination of what is lambda, and how to test lambda, and what we're actually testing. So it was just a very quick introduction. And yeah, I mean, the other option is that actually lambda is way lower than that. So we're interested in lambda, which is basically in between the range that we can either test right away, or we will be able to test in some foreseeable future. And we know that if new physics is at this scale, then this new physics cannot be generic, exactly for this reason, because we know that from the plot before, there are many more effects that unfortunately will exclude this situation. And yeah, so the question that we're asking, and which I will try to give some answer, is what is the space of theories with lambda close to the TV, and how to, at least in some concrete setup, parameterize and describe this space of theories. Does it make sense? And there are basically two options to do that. One option is, let me also emphasize, sorry, this is a very technical question, not only theoretical question. It's technical in the sense that we want to have a framework where we can specify the theories, and then we can match these theories with the experiments, either indirectly or directly. So one option is just to rely on FTP theories. And as we all know, FTP theories are quite generic. They're also too generic, meaning that, as we will see some later on in details, some framework FTP theories, one of them is called linear violation, and we introduce it later on, is quite effective in some UV realization, and is not as effective in other UV realization, as I will show. Another option is to explore these theories just by going model by model. So we can just write down our model, check our model with the experiment, and try to draw our conclusion. And what you will see in the rest of the talk will be a sort of hybrid framework. So this is just to say that the framework we follow is that we write some field theory for some concrete BSM models, so that you can take it seriously up to some uncertain factor that comes really from the field theory. But the purpose of this is really to encapsulate in a field theory the main feature of the BSM model, so that we know that what we're missing has to be small. And this framework will allow at least to go systematically through the space of theories, and will be generic enough to test systematically, as I said, the set of theories. So in particular, I will focus on composite Higgs model, and the concrete question that I will ask in the rest of the talk is, starting with this hypothesis, which is the space we're testing, which is the space we will test, and the space that we've already tested that we will never test in our lifetime. Okay? And if it makes sense, this is the outline of the talk. Yeah.
Okay. I understand your motivation. You want to study the TeV scale flavor EFTs in an organized way, so such that they're motivated by BSM standards. But then you specify you're studying composite. Composite model. So then why don't I just follow the first
approach,
which is the BSM specific?
I mean, composite model is a very broad.
Sure.
Yeah, I mean, basically, I mean, I will describe it later on, but the assumptions that you make are quite little. And of course, it is a concrete scenario, but it's a quite broad scenario. And of course, you can follow the first approach. I mean, for composite model, there is also the problem is that you hardly have a concrete theory where you can compute everything order one. But if you want, the motivation was really to have a sort of map between some theories or some class of theories. I keep calling it class because I guess it's, is not really a precise scenario, but it's quite broad, and basically the data. Does it make sense?
Are you going to correlate it with getting a right Higgs mass as well?
Right Higgs mass, not really. I will not go through it, but you will probably be able to from yeah, but not much.
But you're not going to mention
tuning a little bit. I mean, I can mention later if you want. No, I mean, actually, yeah, no, because I mean, I don't time, but actually, tuning will be, I guess, of order of percent or slightly more. Percent. Yeah. But yeah, I didn't want to talk about tuning. Yeah.
Flavor version of the suit study.
Yeah. That's it. Yeah. If you want, okay.
Why you have uniformly violation
You don't. I mean, sorry, you have mean correlation, meaning that usually you can just assume that suit is completely blind to flavor, so you don't care about flavor. Sorry, this is just to say that when we talk about mean correlation, it's not it's a two-page statement. Actually, it's even better than we see better with composite Higgs. Different composite Higgs model, they have different with the same correlation structure. They will have completely different kind of constraint, and they will produce completely different kind of effects. So if you want, this was just an invitation to say that, we have to stay in the middle. If we just go on one side, we lose a lot of what we want to do. Okay. So, okay, this is the outline. And I have to say that the first part actually will be quite a review. I needed to basically discuss the second part. So I need to apologize with the expert for the first part, and we need to apologize to the non-expert for the second part of the talk, which will be slightly more technical. And let me just say what we mean in this context about composite Higgs and why also it's quite broad, as I was saying. And the assumption is very easy, and the Higgs is composite, so we pick it up from the standard model, that here we call elementary sector, and we put in another sector that we will call composite sector. Okay, so in the elementary sector, we will have our standard model fermion, and in the composite sector, we will have the Higgs plus other states. It will be a different theory. And the two sectors can, in principle, interact through gauge, all gauge boson, so all the standard model interaction. And basically, we are just asking to our theories to satisfy these 4/5 bullets. And the first one is that the composite sector is responsible for the symmetric breaking. This is just if you want a motivation to study this model and why this model is more interesting with respect to others in this context, but I mean, for the phenomenology, you can actually just not care about this and buy the model as it is. It will, so from the first point to the second, naturally explain some hierarchy between M star, which is the mass where this model will show up, and some UV cutoff. And what we just care for the phenomenology is that at some scale, this new sector will confine and will deliver a bunch of references that describe all our phenomenology. And again, these are sort of bonus points, meaning that they are more for motivation and they are more related to the, if you want, the hierarchy problem, is that the X has to be a composite non-Wilson boson of the sector in order to explain why the X has to be way lighter than M star, which again has to be at least PV or more. And of course, the model will come instead with some fine tuning that, I mean, at this level, we can parameterize just by F versus V, where F is the decay constant of the X from the new sector. So this is just an introduction, but just for the phenomenology and for the rest of the talk, what we care is just about this, okay? So in particular, what we care is that the sector can be described, and this is an assumption, and this is the only assumption that actually we're making for the phenomenology, again, by one scale and one coupling which is below 4 pi, so that we can use NDA, and one scale. Since we can use NDA, we can characterize all the effects, starting from the field, or the references, the X, and the two parameters in our game, G star and the scale of new physics. And all these quantities are dimensionless, so we can just expand this Lagrange and get a different interaction. We live well below this point, at least for the moment. So we have to integrate out these references. And what we get is now this effective Lagrangian that, as usually called Filch, that describe all the interaction of the X in this sort of framework. So as you see, it's a theory, I agree, but it's quite generic at the end. Okay? And these are basically where we are right now. If I just write this theory, these are the theory constraints. And as you can see, there are different channels where we can test whether or not the X is composite. As you know, there is the usual t-parameter bound from left, but we're going to assume custodian in the rest of the talk. So for who doesn't know that, but it's not important. And then the most important thing is that we can test whether or not the X is composite from its decays, which are usually parameterized, I mean, described by this operator. We can test if the X is composite from the S parameter. So again, how the X interacts with the gauge bosons, or again, how the X interacts with the gauge boson through the propagator of the gauge boson. And this result, if you want, in this picture, that tells us that this model is excluded up to order of few TB. Okay, really few.
Of the compositeness of the Higgs, because but so far this is to some effective Lagrangian, and suppose I see something from the zero operator, it may come from relating the second.
Absolutely. If you have only one operator, it's probably quite hard to deduce whether or not it's composite.
Is there symmetry between the coefficients that would tell you that this is a composite Higgs?
This is the effective Lagrangian we're writing. As you see, it's not completely generic, but it's always driven by one scale and one coupling.
Okay, but then if the coefficients in front of the individual operators,
they are theory dependent.
There is still can be
absolutely, absolutely. So the assumption we are making is that these coefficients are order 1, so NDI works. But I completely agree with you.
Doesn't smell like there is a new test that you can perform and say, oh, well, this is then a signature of compositeness of the Higgs, other than, you know, just integrating out some heavy degrees of freedom, right? So
yeah.
At what stage can I say that this is a composite Higgs? If I stay at a low energy, not accessing side.
You need probably one more. I see your point. You need more than one operator, and you start to need to relate them. Of course, to answer your question, you need to have a complete theory if you really want to know the coefficient in front.
Right.
So for that, you need to integrate out a precise sector. So if you want, these are pattern of a composite sector. These are
So you
pattern.
can say that this would be consistent with composite, but not.
Exactly. Exactly. And I mean, now that we go later on, I will characterize more this theory when introduce flavors. So of course, then the theory becomes more, stringent in some sense. Okay.
I would say
Yeah.
more positive. If I look at this,
Yeah.
slide, I consider three operators.
Yeah.
The bottom three. There's a hierarchy thing. So if I observe the
Yeah.
in them, the strong coupling, the leading multiplicator will be an OH operator, which is G star enhanced. And
Yeah.
the other one will be G star suppressed.
Yeah.
So the pattern, if I can extract
I mean, that's it. X is part of a strong sector if you want. So you're integrating now some heavy resonances, and the X is one of the strong sector. That's what you can conclude. Does it make sense? Or
So in some sense, you modify the Higgs wave function most strongly, right?
Absolutely.
Yeah, the gauge.
Yeah, I mean, of course, you also see that basically you're producing just these two operators, not many other operators at this stage. So that's already, if you want another hint. But yeah, if you want to,
Yeah, I think
yeah, that is
there's a
this
copy
one.
of the star on operator, so you get a sense of pattern.
So
No.
double is new and it appears like that. It's probably also related or something like that. I don't know if you can gather that in 3 level.
This is 3 level.
3 level?
Here, everything is absolutely 3 level. The only thing that we are suppressing at 3 level is OT, because otherwise it's too large. And this comes from loop, and we check that in all the models that I'm going to present, it's going to be suppressed, the loop effects, but it's model dependent. So just forget about it for the moment. And actually, now this was a fun fact. Next slide, which answered exactly the opposite question that you asked, whether or not you can say that it's not composite Higgs. And because there was an anomaly in the W parameter, so it is just a fun fact, so don't take it too seriously. Also because there is an atlas measurement which basically says the opposite. But there was a CMS analysis which found W less than 1. W, if you want, is the coefficient of this operator here. Now, in the same moment you write down this operator, you realize that there is some positivity constraint on this coefficient, and this coefficient has to be greater than 1. So if you want in composite Higgs, you already see that if you get W less than 0, doesn't work pretty well, and you're probably testing another theory, assuming that you measure. To say that, it's just a 2 sigma anomaly, and actually it's not even completely in agreement with Atlas. So, okay, that's a theoretical exercise that we did, but in case we'll likely move the constraint instead of discovering, we'll exclude even more.
The positivity requirement is not from composite Higgs, it's just.
Yeah, but the requirement just comes from the fact that you define this W parameter. I mean, if you want just come from this operator, some assumption you're making on the UP sector. So you basically, okay, now it's a little longer story, but composite Higgs comes together with this class of theories that satisfy this positivity requirement. It's more generic than that. It's more generic than that. Okay. I mean, if you want the minimal answer is that you have this sort of constraint every time you say that the new sector is heavy, and it's also a standard model only through gauge. That's enough to conclude. Okay, and composite Higgs is one of the, yeah, it's more generic actually. It's more generic. Okay, and these are basically the future constraint that see at the end of the Lumi. So you're basically moving towards eigenmasses. We will test with the Higgs coupling with the Lumi, and yeah, maybe this is the most interesting one is that we will improve a lot from that, just testing proton-proton producing 2W. So really testing this effective interaction here. Okay. Yeah. Yeah.
Like this d mu w mu.
Yeah.
Maybe I can replace it on the equation of motion.
Yeah, that's what you do.
And then why wouldn't I get OT out of this? Because on the equation of motion, if they, like I said, at least in the standard one, or the Higgs is also charged under SP2, so B mu or W mu.
I mean, but you will get it with a different counting, right? So you see that you have basically 4 X's. So in this model, it's very large because you have a lot of X's. X is very composite. This operator instead there are only 2 X's and 1 gauge. So you see that the scaling of the coefficient is different. So what you're asking is is surrounding effects?
But
Yes.
it will lead to P parameter, right?
Yeah, indirectly. Yeah, indirectly.
But you say it's.
Yeah. Smaller, yeah. Okay, and finally, let me say that we can test this scenario even directly. Of course, actually, there was this measurement earlier this year, later for this talk, that basically tested production of WWZ. You have to think about them as longitudinal, so they're basically releases from rho, where rho can be some composite spin-one resonance from the new sector. So the idea is that you can, if you are as low as 4 in QTD, you can actually directly produce some state in the new sector that eventually decays in WWZ, and you can measure the bridging fraction. And so this is just a picture to say what is right now the status. So this line comes with a very small residual model dependence, but I guess you can take it order 1 in this plot. And you can see that basically everything is excluded from 2, 4, roughly between 2 and 4 TB below. Okay. And there is one last effect that I have to talk before talking about really flavor. And these effects come from the so-called Weinberg operator. So for the moment, I didn't talk at all about quarks, but I just talked about gauge. But at the same moment, we say that the strong sector is colored. Basically, we can have effects of this form. So we can generate this operator that eventually produce a non-zero dipole for the neutron that we test very well. And this results in an extremely strong constraint, which is basically this one, that combined with the Higgs coupling basically tells that M star has to be larger than 10 TB. So this is the first hint that if this sector is there, it has to be CP invariant, even without talking about quark at all, okay? Okay, good. So now we have to move to fermion. I was missing something quite important, which are the Yukawa interaction. There are 2 ways to include fermion in our game, and so to generate the quark masses. And the first way is what's called Technicolor, all this Technicolor, which is basically just including a Boolean interaction between the standard model fermion and Higgs or Higgs operator. And the second one is what is called partial compositeness, where basically the standard model fermion, they mix with the with some composite operator, and in this way they produce the Yukawa from mixing. We have to choose one of the two just by a matter of time. The first one is quite harder in general from model building perspective, and so we basically in the rest of the talk just focus on partial composite like interaction. So when we think about the mass of our fermion, what we have to think is that the fermion, they interact, they mix with some states of the heavy theories of the strong sector, and the strong sector contains these, and in this way we generate the interaction. So this means also that we have completely to change our effective Lagrangian, and this is actually where we start. We did something sort of new, meaning that we start systematizing all of these, and the way we have to change it is also including the mixing by the psi of the elementary fermion, so our quark, for instance, or lepton, and the resonances that mix with the quark lepton. Okay, this was all known, and basically starting from this Lagrangian, we can integrate out again the heavy resonances, which we have to imagine to be TB or more, and come down with a new effective interaction. We also include the quark.
So these are
Yeah.
vector-like resonances?
They are vector-like. They have to be massive. Yeah. Yeah. Then okay. Yeah. Let me say that this seems quite simplistic. As you see, apart from the mixing, there is one coupling and one scale. So we know that it's very simplistic. We have to say that we also tried, and we show in the paper that you can try to do something more sophisticated, where some of these guys here are mesons or a glue ball, and the X is glue ball or meson. So to have more different Lagrangian counting for the different species of resonances, but we didn't find basically any phenomenological difference at the end. So yeah. Yeah.
In the first Lagrangian, inside parentheses.
Yeah.
Shouldn't I have a G star instead of lambda psi?
And the psi is an extra parameter which is this mixing. Okay. So it's not, if you want a strong coupling, okay? But it's just measuring how much these guys mix with the strong sector. If you want, when lambda is 0, you're saying that it's either completely elementary, and so they decouple from the sector. But if you want, lambda is measuring how much it can, access through the quarks the strong sector.
And you would say that you want all your interactions to be not waiver violating?
I didn't say any more level.
Well, I meant at the start.
Sort of. We want to characterize which are the kind of flavor structure that we can have.
Okay. Are you gonna impose the big line?
Yeah, the rest of the talk. No, I mean not flavor diagram. Sorry, we are going to impose some symmetry on this lambda.
Okay.
Yeah. Okay, give me a few slides. Yeah. Yeah.
Whenever you want to write down the for the strongly coupled variable energy, is application NDA, does it always works? Right?
Say again, sorry.
Does application NDA 9-dimensional? This is 9-dimensional.
That's a good question.
I mean,
not always.
We know that works for prime, so that you have a hierarchy between.
I mean, not always. We know that NDA doesn't always work. In this case, I mean, there are not many lattice calculations one can rely on. There are holographic models that have been checked in details and that produce this effective Lagrangian. If you want, it's an assumption that you make that NDA work.
Careful. So they have to be operator by operator, think about all the symmetries.
Yeah, I mean, that's true. But of course, in a coefficient, if you take a suppression, which is of 2 order of magnitude, unfortunately, this you cannot predict at this stage. Okay. But I mean, again, the idea was to broadly span, if you want, the space of these theories. So if you want at this level, we're not asking about this kind of details. Okay. Okay, so now we have to talk about flavor. Yes, I'm going very slow with time, but let me try to say it. And so, I mean, there are different options, and these have been, quite studied in the literature. I wanted to review them just to update the bounds and see what is the situation now. But the minimal option is to say that you have no flavor symmetry. This is called anarchy. And the beautiful part of this theory is that basically you don't have to do anything. You just say that you have this mixing, as I described before, and that you can reproduce the correct Yukawa and the correct signal memory. This is enough. You just say that, and you fix up to order 1 factor. As I said before, all the various lambda, and what you get is that you get for free that you have also many flavor relative processes, because as I said, if there are no symmetries, there is no reason why the composite fermion they cannot interact. So all the interaction you can imagine, they can be mediated by some exchange.
So
yeah.
You couple the standard fermion to some of this. So I don't know how to put
Partners, yeah.
Those have an additional, do they have an additional gauge interaction that leads them to be?
They can. Yeah.
Yes. Okay. Then they should be part of some sort of a variant, right? Because you cannot take the electron
I mean, they are composite. I mean, if you want to have a mixing, yeah.
I should be thinking of these thick lines as some sort of a variant in that sector.
Yeah. Maybe variants that mix. I mean, if you want, I mean, the example is for gauge. I mean, for gauge, you think of mixing.
Yes.
Like we have, spin 1 and standard model gauge mixing that we can imagine with also PCB, and here you have to think about the same for variants. Okay.
And this mixing doesn't violate any gauge symmetry, or you have to insert some.
Everything. I mean, these guys is the same gauge quantum numbers in the standard model as our work.
Okay.
All of them. So basically, you just copy them and then you pass some extra structure. Okay, so basically, there is a bonus also, but probably not skip is that this is really an actual theory of flavor, and has been shown to the expert in the audience, and that also even with this pattern, you can also predict the correct masses for the standard model quarks. But okay, let me just tell you what is the result of the constraint right now. And the result is quite severe. The bosonic operator, the one that I described before, you see the plot, but just focusing on the quark sector, you see that through the new flavor-relatable observable, and particularly epsilon k, you get a bound which is extremely strong on the composite sector, which is more than 20 dB. And even worse is for the neutron EDM, which is between 50 and 80 dB. And even worse is for the lepton sector, where you get almost 2000 dB from the electron EDM, if you assume that also the electrons are composite. Now, we can try to cheat as much as we want. We can say that the lepton sector is not there. And so there will be new physics to explain the lepton sector. We can say that we have some symmetry that and the parameters, the so-called Kushner symmetry. We can keep after the bosonic operator, the one that I showed before, the Weinberg, assuming CP. But we are still left with quite some severe bound. Oh, we can also say that neutron EDM are suppressed by some loop. You say why loop? Because in holographic theories, usually it happens, and it's an extra assumption. So I'm trying to put all the cheat again. And if we put everything together, we still see the violation in the strong sector, but we can still be through the mixings. Okay, because you still have to explain the CP phase in the standard model, so the mixing has to be complex in general. And if I don't find another way to kill them, you still get okay. And so the result is basically the following: is that M star has to be as large as 20 dB. So yeah, I mean, it was for the moment just review these all theories, but what I get is the base excluded right now. And if I also put the update from Illumi and the next 20 years of flavor experiment, this will go up to 40 dB. So we'll be probably out also of the SCCH reach. Okay, so starting from this, that's what we ask is, yeah. I mean, yeah, I was just trying to put, you know, kind of cheat that we can do as a BSM theory. It was just a motivation, yes. Yeah.
Is that consistent with the counting in this?
You put some of the lambda to 0, and then this lambda you have to explain somehow in a different way why they get mass. Okay, and why they interact with the X.
Let's say I did that.
Yeah.
I said the 7 leptons.
Yeah.
But here you have the dipoles loop order, right? Transported from lepton sector.
It's not enough in the lepton sector, this loop order, yeah. That's what you're asking, sorry?
Since I said lepton sector, right? You should expand more suppression.
No, this is, sorry, this is a strong physics loop. I'm saying that, assume that you can resolve this from dynamics, and the only way you can do it, I guess, for the moment is with a holographic model. You compute this guy, and you see that the coefficient is accidentally suppressed by one loop factor. This is something that happens sometimes in some theories, and I was just putting it by hand to say. The theory where this is suppressed, it's true.
I'm saying that the neutron could be also suppressed by
yeah, I mean, I know that is dependent on the assumption that you make. We want it to be as generic as possible, at least in our limits. And so, you know, this extra factor, I just put it in the slides, present, you know. But of course, you can try to design a more complicated theories, but then you are, if you want, losing the original purpose of spanning in a broad sense of the theories. Yeah. Yeah.
So what about mu conversion?
It's way below that. It's way below that. Now we don't even get the number of in nuclei. I mean, it's going to improve a lot, but for the
you see, the scale is high, so this is a high dimensional operator. It's gotta be like a 6 dimension 6.
that's going to dimension 6, yeah.
And this is maybe dimension 5 or
I mean, I can tell you the exact number later on. Now I forgot, but we checked, and in the anarchy compositeness, we checked all of them. In anarchy, these are the leading two bounds. Yeah. I mean, I also have to say that this is going to improve a lot. Now, I will not talk much about leptons, but it's going to improve by basically 4 order of magnitudes, the mu2e conversion in nuclei and mu2 So at some point, it's going to become important. Okay. So what is the way out? And the way out was proposed long ago, and the way out is basically very cheap in some sense. It's to copy the standard model. we know that the standard model works very well. We know it works very well because there's tons of symmetries that we believe to be accidental, but they are there. So we can try to do the same in the new sector. So basically, we can try to design a sort of G mechanism where we have a lot of symmetries, but now in the composite sector. So this is a little this is important. We cannot touch the elementary sector. We are only making assumption here. So when we say that we impose symmetries between these guys. Okay, so the elementary sector is completely untouched, and the most simple symmetry we can impose is what is called minor violation. So that if you want this term times the elementary is just the flavor symmetry group of standard model without just with the 3 quarks, without this, and is broken by the lambda of the mixing up to the one model. And what we will show is that with suitable flavor symmetry, M star can be as low as TV. At the same time, so this amount instead we are losing some of the predictivity, meaning that now you have to design a new theory of flavor. So this can explain why you have a mass as low as that, but you cannot explain why the lambda are so small. At least this requires extra model building that I'm not going to discuss. Yeah. Yeah. That's the idea. You have a sort of U3Q in the bulk if you want. And the standard model, I mean, sorry, this is the standard model, yes, but basically the breaking comes from the lambda breaking. So I really the mixins that are breaking, they probably put on the boundary. Okay, so that's the yeah. Okay, so this exercise has been done. So again, I'm just updating, and this is just a boring slide to say that you can do it. There are 5 different ways to do it, depending on your content, and it's quite systematic. So you can just be there and try to match the symmetries in order to have the final pattern, which is the same as the standard model. So let me just try to mention one of them. You start with the G-strong, for instance, which is, I'm just talking about 4, U3 up times U3 down, composite up invariant. Now you assume that some of the mixing are completely diagonal. Okay, so for instance, the right-handed quark, for right universality, the right-hand standard model quark are completely aligned with these guys. So even after the mixing, you have still the symmetry, which now is a U3 up capital times a plus small up. And then finally, the mixing of the left hand will be break everything to the standard model. And so they must be proportional to the U cap of the standard model. Okay, now one can do the exercise properly. And I'm just going to show the plot of these 2 guys. The only difference is that in the first case, I assume that lambda up and lambda down are diagonal. So you think that basically the right-handed standard model quark are completely aligned with the global group of the strong sector. And in the second case, we'll do the same for the left-handed. And the result is, okay, so if you want, this is roughly the assumption, the answer that we are making for this Fourier. And the result is that is basically, let me just show the final number. Again, we encounter quite some constraint. It's way better than it did before, I have to say, but there are still quite some constraint. You see that you don't have any port dipoles, and the reason is that this theory is basically as good as the standard model in terms of flavor. So in the standard model, we don't worry about dipoles. I mean, dipoles are very small. They are suppressed by the G mechanism, if you want. Sorry, not the G mechanism, by the fact that you have only one angle, one source violation. And the same is going to be in these theories, and you can show that no EDMs are there after 2 loops. You have no dipole flavor violating effects. The interesting thing is that, as I told you, the elementary quark are completely aligned with the composite quark. So this means that also the late family are basically completely aligned with the heavy family. And this means that if the top right is very composite, also the upright is very composite. But we know that the up behaves like an elementary particle. We test up quark every day at the LEC, and they behave as elementary. And this is, if you want, the result of these first 2 lines. That they just searches, they tend to say that epsilon up, which is how much the parameter that controls how much the up quark is composite, that they prefer very small composite quarks. But at the same time, when they are very small composite, we are sort of making composite the other side, the left-handed, and we go back to flavor violating observable. Okay, so I've been very quick, but if you want, the result is that in this theory, you basically have no freedom, because you are saying that all the standard model quarks in up, right, and down, right, they are part of the same sector. They have some huge flavor symmetry that relates them, but we know that we don't want to modify much their quark, and not even the down quark, because we know that they behave as in the standard model. So the final result that I show in a plot is basically, okay, let me just, that if you combine these two effects, so flavor violation and compositeness, you get again a bound which is of few or more TB. And the same up in the left and the sector that I'm gonna skip, but this is basically on the phonological result. So let me start with the right, which is the theory to describe. There are two lines. In one line to the other, we did some additional revision, assuming some custodial protection for some of the coupling. I didn't say to, if you want, part of the game was to use all our to justify how many assumptions we have to make to get a lower scale. So take the solid line, which is the one where we have no more trick to play, unless we make really a specific assumption on the view sector, on the coefficient of the effective field theory that results from the view sector. You see that basically everything is tested up to 7 or more TB. When you try to be more generic, you have to start playing even more effects. In this case, the estimate becomes important, and the bound becomes even stronger. It's interesting that on the left side of the board, I'm showing instead the same, where we make the same assumption, but for the left-handed quark. In this case, we are modifying a lot left-handed quark. This means that we modified a lot the W couplings. And again, W couplings are very well tested. And you see that you get a Toscan which is well above the various searches.
But again, this is assuming that all generations have the same cutoff, right? Because most stringent bounds come from the first generation.
Absolutely.
So you can relax that as well. I think you have states which are much higher.
That's the next part. Yeah, I mean, that's absolutely the idea, is that you see that there is a sort of systematic way to do it. And so we have.
It's just symmetry. We're just trying to.
Yeah. But I mean, I mean, if you want, this slide sort of summarize what we are trying to do. And basically, we started with this Lagrangian, which is if you want to pick the mixing Lagrangian that I showed at the beginning. And then we start asking a few questions. The first question that we ask is, can we put some flavor symmetry? And we started with 0 flavor symmetry, and it didn't work. Then we started putting the maximum number of symmetry as much as the standard model, and it didn't work. And so one can try to relax the symmetries. Then there is a second step. How do the mixing break this symmetry group? So standard model can assume. Then we said we can start with this symmetry group and just say that the right-handed are aligned, or the left-handed are aligned. And we try different options. So this is an extra degree of freedom that we have. A last one that I didn't describe, just a matter of time, is that we can have other symmetry that is what we call vertical symmetry, but there are some extra symmetry we can impose at the level of the theory in order to suppress some more effects. And only one is own, which is called PLR. If you want this Z2 symmetry that comes for free in many realization of these models, but it's an extra symmetry that we're putting by hand if you want. And all these options generate a landscape of possibilities. What we did basically is to systematically go through this landscape of possibilities till we found it worth doing it. So if you want, we started with the mean relation with all the right-handed quark aligned, and then we start breaking the symmetry down and down again. And we did the same in the left-handed. And for all these options, we went through to see which other assumption we can make on the V sector. So for instance, are dipole generated at one loop? Are they generated at 3 level? Do they have further suppression, or do we have accidental vertical symmetries? And all of these, if you want, resulted in this sort of picture. And where basically, if we put on this axis the scale of geophysics, we see that the minimal model, the anarchy model, is well below 42 plus TP, so probably we'll never test it, at least directly, maybe indirectly. Instead, only few models are in between the scale that we can test at the LHC, and at the same time, all the models that we tested are in between what we can now and what we will be able to test actually colliders.
Where the time it's supposed to be, 120.
Yeah, I mean, I took it from the same way page, so.
So I'm seeing a picture where I'm like, further north, further that way.
That's, I don't know. That's, I'm prepared. Yeah, so that's basically the picture that we got. And let me also emphasize again that basically the part of the game was also really to be systematic in a way to provide a map. Okay, a way to provide a map that experimentalists can check systematically, and for each one of these options where the leading observable can give a signal, whether they cannot. Now, in the rest of my time, I'm trying to describe one of these models, at least just to tell you what is the phenomenological feature. If you want the model where we found the best, if you want realization with the data, is an intermediate between having no symmetries and having all the symmetries. What is the most obvious model that you can imagine? Basically, we have enough symmetry to say that, for instance, all the down ports, they are aligned with all the down ports in the model right-handed, they are symmetric, but at the same time, we can separate the first two families from the top. Okay?
So you want to lower the scale.
We want to lower the scale. I mean, at least we want to see what are the options. Yeah. And this seems to be, at least to us, the best option. And then we tried also to go further, but we see that reducing the symmetry then introduce extra parameters. This is important, right? That you see that no symmetry doesn't work, or symmetry doesn't work as well. So there is, if you want a sweet spot, that is the one that we can test. And I mean, I just show you the plot. Yeah, maybe this okay to show. And what we see is that now the first constraint, like composite plus that work, is perfectly fine, because now the first two families, they are disentangles from the top. So the top is very composite, the first two families are not very composite. Quite obvious, but it works. At the same time, dipoles are quite fine. We still have a lot of symmetries. So we don't have many phases which are physical. Many of the phases, they can really integrated away by some filter definition. So this is not as efficient as the standard model, but EDM, for instance, they just show up at loop. This is not loop of strong dynamics, but it's loop of lambda, so loop of the standard model dynamics. So loop of standard model quarks.
So top answers.
I mean, if you want, I mean, all the coupling, they can be complex. What we're asking is that now you compute the dipole, you have a lot of Fourier definition. Can you do a Fourier definition so that you bring out? So, I mean, do you have flavor invariant phases under the strong dynamics?
The Higgs, like is the phase of the top, the Higgs coupling to the top and to the electron.
You have to see whether or not.
Then there's two.
I mean, you have a lot of, yeah. I mean, if you want, you have to go through in detail. There are many symmetries, so you have to see, where are the phases and where you can bring the phases by symmetry. So if you want, as in the standard model, we know that we have to go to several loops to see the phase. Here we see that, for instance, in 20M, you need to go at least to one loop. And I mean, just let me emphasize that the down sector is basically completely aligned with the standard model. So you need really a loop that connects the up sector with the down sector. Because in down sector, you have a U3 symmetry that is pretty much, we'll go ahead.
If the top has
But here, I mean, if you want, we start with all possible phases. So the top has a CP violation. Yeah.
Let's say it's a two effect because
We found it at one loop. I mean, there are also phases in the up and down. So the phases are everywhere. Yeah, actually, they come from the, I mean, now I didn't want to go through because, I mean, I'm late with time, but, the exercise is the following. You write down all possible mixing, and we see now that you have U2 times U1. Okay, for the right-handed and for the left-handed. And all these numbers, A and B, they can be complex. And they are the only two complex numbers up to Fourier definition. So basically, we did all possible Fourier definition to bring two phases only, here and here. So you see the T2 mixing, they have two phases. And now you can ask, can I write, starting from this lambda, any combination of flowing invariant objects at the end in the dipole? And you cannot. That was the exercise that we did. You need also the down sector. And yeah, so if you want, you don't have dipole, you still have some effects, but this is pretty much the result. And the result is that for this model, and then you have to ask whether or not you find it plausible. There are basically no constraints. Again, we choose these two options with one additional level symmetry, one with less. But at least the optimal one is pretty safe. The other one is still very well constrained. But at least there is one option which is well below the direct reach. The universal, the one we showed before. So this is Higgs coupling.
Or is it still Higgs?
Yeah, they are all Higgs
Oh.
physics. Yeah.
No.
And yeah, then there is another question they want to ask. We started. We sort of tuned, right? We started with some generic model, then we had symmetries. Then we found a new theory in function of some parameters. Now, this parameter, at least for this point of this order, now we want to ask whether or not you can find a new realization where this parameter can be constructed. Okay, so this is a point that I want to emphasize, is that it's not obvious that any of these theories can be constructed from a new theory. Our job was to find all the possibilities and to list them and to give a framework where we study these theories. And then as a model builder, the next question is to ask whether or not these theories can be realized. Okay, so since
Let's just add this up.
Yeah.
Right. Compared to this universal constant which you're showing in the very
This
beginning,
one.
right? Yeah. This study of flavor with this clever
Yeah.
composite assignment that was compared to that custodial protection, only it enlarged the excluded regions by this blue, dark blue region. So
which is basically almost
just a little bit.
just a little bit more.
Yeah. So you're claiming smarter design flavored composite models.
Yeah, I mean, it's really smart design. Also, I mean, part of my talk was also to really explain the kind of assumption we made, which are mostly based on symmetries and then to recast the standard model. We didn't make any further assumption on the, I don't know, some specific coefficient which is not there, or some specific effects which is not there. It's really only symmetries, and also these two options are actually symmetries. Okay. And okay, now I don't want to go into detail of all the other models, just show that you can go further and imagine that you have even less symmetries. So before there was a new tree connecting the two down and the bottom. And now we can relax it, and the picture is pretty much the same, but now you see that it's quite harder. You need to make even additional symmetries to go to scale which are below the direct reach. So this is just to say that somehow this clever setup is the sweet spots where you are close enough to the standard model, but far enough to to have very strong sector in all the generation to not have any other kind of a constraint. As soon as you start relaxing even more the symmetries, you start to be more generic, you get worse somehow. And then you can still try to do extra model building, but of course now you're losing of generality. And there is a similar picture also for the left-hand sector. Okay, and this is roughly just let me tell you how this situation is going to improve. I just proved the best model we have. In basically, there will be a sort of improvement in delta equal to transition. In our case, the linear effects come from BD, but it will be sort of complementary to also universal constraint. And of course, also, I mean, Ctn operator is ds to mu is going to improve. These are the two first models that they show. So the one where we have all the flavor symmetries, they will also improve a lot. At least at the left side, you can see that the jet bound improve. We're going to produce one more jet, the LAC, and the same will happen with flavor. On the right plot, unfortunately, to say that we don't know how much this is going to improve, because the decoupling comes from the CKM unitarity, and we didn't manage to make an estimate. So there's just an arbitrary factor, but we don't know how much it's going to improve. But what I want to show is that both scenarios, they are within the SCC HH reach. differently from the anarchic. So some symmetry seems that we need to assume symmetry if we want to at least observe anything, or the other way around. But and these are the traditional models. They show that, as I said, they're going to all improve the bounds. They will definitely go outside the LHC reach, but they will not go so outside the FCC. Now, before concluding, let me just say something about leptons. We didn't say anything. And the same works for leptons. Also, leptons, they have to be composite if we want to explain the small masses of the leptons. The largest constraint comes again from EDM. In this case, I have an EDM, which is more than 2000 TeV. And then from UV gamma, that's what we found, at least in the scenario without symmetries. Now, for leptons, it's quite easier. With symmetries, they work very well, basically to get rid of all the dangerous effects. And actually, what is called lepton minimal violation, where you, for instance, say that all the leptons, they are composite, works extremely well, meaning that you get rid basically of most of the bounds up to dead coupling from left. And this bound, you see that compared to the one I was showing before, they are quite mild. Take the G star and then from 1 to 4 pi, you have a lot of space for MS star will be well within reach, or at least competitive with the other constraint I showed before. Yeah, that is basically what happens for leptons. Then you can try to do the same game that we did and to consider a less constructed scenario where you have less symmetries. But what we realized that as soon as you do that, you incur new constraints. And so it is really not favorite. Or, I mean, now, if you want to revert it, the mean of revelation is very hard to test. In this case, it is easier to test it. Okay. For the neutrino mass is a good point. In this way, we cannot describe neutrino masses. So usually what is done in this sort of model, you include some sort of linear interaction that explains neutrino masses. So it's a different kind of physics.
Not in this.
Still in the composite sector, but not through linear mixing. That's one of the options. I mean, this is more model building side, so I didn't say anything, but there are different. You run a direct masses, you can split the two, and
very small.
exactly, that's another point. That's, I mean, yeah, this has been they've been worked out, especially in extra dimensional model, all these kind of possibilities. Yeah. Okay, so since I'm late, I guess I'm gonna conclude. I mean, we did also another exercise, and now I'm not gonna present, which was to basically with people in area to try to write a model in 5D that can complete any of this picture. We're still working on that. We end up with a very complicated picture where we have many CFT that with many confining phases, but at least we seem to have a picture where we can basically realize one of this model. This model building is more complicated, so you know it's a different task with respect to what we said before. That's what we are trying to do, and we have some results. I'm not going to talk about that. Yeah.
What's in the UV? Just all elements?
I mean, what we try to work is really a sort of holographic theories as the standard that you know very well.
No, but do you have fermions or just fermions?
Yeah.
UV and nothing else?
I mean, you have the full holographic theory, so you don't need to refer them. I mean, so let me just say what is the difference between why the writing an holographic theory is slightly harder than usual. It's because, you know, usually we generate the hierarchies starting from the same dimension of the operators. And now the operators, they are all symmetric. So you cannot give different same dimensions that give you different masses. So basically what we have to do is to write a new sector, which is really in the value V that generate the masses. And then this sector decouples and the second sector does the rest of the running. And there are two tasks that this theory has to do. One is to generate the mass. The other one is to justify why, for instance, the retended quark in some of the scenario, they are very aligned with the composite quark, because this doesn't come for free. We took it as an assumption, but in a UV theory, to explain it. And what we are trying to show is that this can be done by the running. If this new fermion, if you want, the elementary fermion are coupled with relevant deformation to the composite fermion, the running itself can make this alignment. And being very fast, but I mean, it's not straightforward. There is some model building to do. And then the question is whether or not anything of this is plausible from a model building perspective. But from a technical perspective, we can ignore all of that. Let me try to conclude some over time. And what we did is basically to summarize, to go really through in detail to see all possible options, at least the minimal option that we can have, to systematically go through them and classify them in terms of symmetries and in terms of some specific assumption of UV sector, trying to be as generic as possible and as honest as possible as well. And what we've seen is that basically, as much as you try to reduce the structure of the theory, so you make simple structure like anarchy, where you don't have many symmetries, the theory is excluded. And when you start adding on to symmetries, at some point you have too many, so the theory is excluded as well. The sweet spot seems to be between, with different kind of additional assumption apart from the flavor symmetry that you have to make on the UV sector. And yeah, then the next question, if you want as model builder, is which one of these is more plausible, which one of these is more interesting. And that's probably it. Yeah, sorry, it's that I can conclude. Yeah, thank you.
Just to clarify, when
Yeah.
you say excluded and model still allow anarchy, it's just a very cheap.
I mean, yes, I say excluded, I mean that you cannot directly test it. In this
Yeah.
sense, for me, it's excluded.
That's all.
We just say we will not see it.
Excluded.
Absolutely, model can always be bad.
Things like that theory is completely wrong.
Correct word would be openness.
That's one.
I mean, actually, you can even test it indirectly. So excluded in, I mean, at our energies, but on the semantic, I agree with you.
Exterior model operators are usually not demotivated doesn't see of the arguments.
Yeah, I mean, it was a bit fast here and probably also a bit too. Yeah. Let's see. I found it. Okay. So, yeah. I mean, the main reason why we focus here is time, because this was just part of the work we did and actually took a lot of time. And so one has to start somewhere. But in principle, you can try to start theories where the bilinear kind of interaction technicolor gives you the work masses. What is actually excluded, or at least extremely implausible, is that this work for the top. And the one that you saw that, and the idea is very simple, is that the top is there, you know, we need to write it. In these theories, what OH is the operator interpolated in the X, and since we don't want to have a lot of hierarchy or the hierarchy problem, you assume that the OH dimension is quite large, so that OH square is, say, almost 4. Okay, because you want it to be as, you know, marginal as possible. Okay, instead, you see that this operator is in the top, and so you want it to be not too marginal and not too irrelevant as well. Okay, but you want it to sorry, not too irrelevant. Now, if OH is very large, OH square is very large, also OH is probably large, and the theorems that when it was quoting just say this slightly more formally is that if dimension OH square is very large, also dimension OH is large. You cannot have a very small dimension for OH with a very large dimension for H squared. I don't know if I've been too fast.
So
Yeah.
just for me to
Yeah, exactly.
this first operator that you were showing you of H delta H everything squared, right? This is your the analog of this is the analog that the Carol PT, this would be something that gives the final scale. So that would be the one not suppressed by 4 pi by
Okay, I saw this one.
this one, right. Right. So what is the current best
That's a good point.
experimental probe? Is this some sort of
I mean, I guess the wish that I guess is not gonna happen is to really scatter for X's through VBF, but I guess the cross section is too small for that. So what you do it is you do indirectly.
That was
No, I mean what you usually test it is through the X coupling. Because if you modify this, basically I'm modifying all the X coupling, so all the X decays indirectly if you want.
So the kinetic term will modify,
Exactly.
will be
Exactly.
absorbed into, and then it will.
Exactly, then you study all the
outputs
decay,
will-
absolutely.
So, but then they probably want a specific sign on that. Does this lead?
No, good point. I don't have any explanation to say why this is a specific sign. And the first one,
Or